Consider this startling statistic. 84% of diabetes-related amputations are actually preceded by a simple, seemingly minor foot ulcer.
Yeah, think about that for a second. It's a terrifying number.
Right. What starts as just a tiny friction point, like a blister from a tight shoe or small scrape, can just cascade into a massive, life-altering medical emergency.
Exactly. And usually we expect medical diagnoses to be these, well, highly visible events.
Yeah, like you break an arm, the x-ray shows a jagged line, and boom, the problem is obvious.
Right. But with this condition, the real danger operates almost entirely under the radar. I mean, the human body is literally built to sound alarms when tissue is damaged.
But diabetic foot disease systematically dismantles that alarm system.
It does, completely. By the time a patient actually, sees a problem, the structural damage underneath is already profound.
And that is exactly our mission for you today. We are taking a deep dive into the literal foundation of diabetic health.
We really are.
By synthesizing the 2023 International Medical Guidelines on Diabetic Foot Disease, some really fascinating recent university research, and a 2026 Industry Guide to Therapeutic Footwear, we are going to uncover the hidden pathophysiology of the diabetic foot.
And the extreme engineering designed to protect it.
Yes. Okay, let's unpack this.
So, to understand why a highly engineered shoe is a strict medical necessity and not just a luxury, we have to look at the sequence of events happening beneath the skin.
Right.
The guidelines outline this specific pathway to ulceration. It basically requires a perfect storm of three elements. First is neuropathy, which is the loss of feeling.
Okay, neuropathy.
Second is peripheral artery disease, or PAD, meaning diminished blood flow. And third is a precipitating event.
Precipitating event sounds so dramatic, but reading through the sources, we are just talking about normal, everyday wear and tear, aren't we?
Yeah, exactly. Like walking barefoot to the mailbox, or literally just a seam inside a sock rubbing against a toe. That is the insidious part. For those of you listening while out on a walk right now, imagine if the heel of your shoe was rubbing your skin raw.
You'd feel the sting immediately.
Right. Your pain receptors would fire, and you would naturally adjust your stride or, just take the shoe off. That pain is a critical survival mechanism.
But diabetic peripheral neuropathy just shuts that off.
It does. Clinicians actually call it LOPS, loss of protective sensation.
So the patient is essentially walking on an injury all day long, completely oblivious.
Oblivious to the damage being done, yeah.
If the body's natural pain warning system is completely offline, how do clinicians even catch these injuries before they escalate? I was looking at the physical exams from the 2023 International Working Group on the diabetic foot, and I gotta say, the tools they use to measure this invisible loss of feeling sound remarkably low-tech.
They do sound basic, yeah. But the physics behind them are incredibly precise. The first line of defense is a 10-gram Semmes-Weinstein monofilament.
A monofilament, like fishing line.
Basically, yeah. Picture a small plastic handle with a thick piece of nylon fishing line sticking out of it. The clinician presses this nylon filament perpendicular to specific spots on the bottom of the foot.
Okay.
And they apply pressure just until the filament buckles and bends.
I assume 10 grams isn't just some arbitrary number they picked out of a hat. There must be a mechanical reason they want it to bend at that exact force.
Oh, absolutely.
Yeah?
The nylon is calibrated to buckle the moment exactly 10 grams of linear force is applied to the skin. Through extensive clinical trials, 10 grams of force was identified as the exact threshold of human protective sensation.
Oh, wow. So it's a pass-fail test.
Essentially, yes. The patient closes their eyes. If the clinician presses the filament until it bends, and the patient says they feel nothing,
then their baseline defense mechanism against friction is officially gone.
You got it.
That's wild. And then there is the second test, which involves a 128 hertz tuning fork.
Right, the tuning fork.
The clinician strikes it, gets it vibrating, and places the metal base right on top of the big toe joint, where the bone is closest to the skin. Now wait. If you're putting a vibrating piece of metal directly against a joint, you aren't testing for skin-level sensitivity anymore. You must be testing the deep nerve pathways that run through the bones and joints, right?
That is an excellent deduction, yes. The pressure from the nylon filament tests the small sensory nerve fibers in the skin.
Gotcha.
The tuning fork tests the large nerve fibers that detect vibration and position. So the clinician holds the vibrating fork to the toe and asks the patient to identify the exact moment the vibration stops.
And if they can't?
If the patient can't feel it, or if the clinician has to move the fork further up the leg, say to the ankle or the shin, just to find a nerve that still registers the vibration, The foot is in critical danger.
It's like driving a car with a completely broken dashboard. You have absolutely no idea the engine is overheating until smoke is literally pouring out from under the hood.
That's a perfect analogy.
So what happens internally when you keep driving that broken car? The guidelines describe this process where the foot is subjected to abnormal biomechanical loading. You walk slightly wrong, you don't feel it, and the body builds up a thick callus.
Right. Building a callus is the body's desperate attempt to build armor against the friction.
Makes sense.
But because of the neuropathy, the mechanics completely backfire. A normal person feels a callus getting too thick, it becomes uncomfortable, and they treat it.
But the diabetic patient doesn't feel it.
They don't. So the callus just goes thicker and harder. It becomes essentially a rock glued to the bottom of the foot.
Ugh. Which means every single time they take a step, that hard rock of a callus is being driven upward into the soft tissue inside the foot.
Exactly. It creates immense localized pressure. That pressure eventually crushes the capillaries underneath.
Ouch.
Yeah, you get bleeding deep under the callus subcutaneous hemorrhage. The tissue literally dies from the inside out, turning into a cavity of dead tissue.
That is terrifying.
And once that callus cracks or is removed by a doctor, there's a gaping ulcer underneath. Now, bring in that second element of the perfect storm we talked about. Peripheral artery disease.
Right, the diminished blood flow.
Blood flow is the supply line for your cellular construction workers, right?
Right.
Oxygen, white blood cells, nutrients, none of it can reach the injury site.
So you have a deep, gaping wound and absolutely no biological resources arriving to repair it.
Exactly. It's a localized starvation.
Which transitions us perfectly to what happens when the smoke actually appears. If that internal warning system is compromised, the medical team has to rely on intense external classification to figure out how much damage has already been done.
They do. They need a standardized language.
And the 2023 guidelines use an acronym to classify these ulcers that I actually found brilliant because of how the factors interact. It's called SINBD.
Ah, yes. SINBD. It stands for site, ischemia, neuropathy, bacterial infection, area, and depth.
Right.
It allows any doctor, anywhere in the world, to instantly understand the lethality of the wound based on a score.
Let's break down the synergy there, because site and area obviously dictate the size and location of the battlefield. But ischemia, the lack of blood flow, seems like the real force multiplier here.
It really is.
Because the guidelines note that diagnosing an infection relies on clinical signs, right? Like redness, warmth, swelling. But wait, if ischemia means there is literally no blood flowing to the foot, then the foot can't get red and swollen even if it's massively infected.
Bingo. That is one of the most dangerous paradoxes in diabetic foot care.
Wow.
The classic signs of infection are caused by the body rushing blood and inflammatory cells to the area. Severe ischemia blunts that entire response.
So it's hiding the infection.
Completely. A patient might have a raging, limb-threatening bacterial infection, but the foot looks pale and feels cold. Add in the neuropathy, and the patient feels no pain.
So what does a doctor even do?
A clinician has to look past the lack of visual inflammation and hunt for other clues, like fluid buildup or deep tissue breakdown.
And to figure out the depth part of SINB, they use something called the probe-to-bone test.
Yeah, this part is intense. The clinician takes a sterile, blunt metal probe and physically explores the deepest part of the ulcer cavity.
They just push it in?
Very gently, yes. They are pushing through the soft tissue, feeling for the hard, chalky resistance of bone. If that metal probe touches bone, the probability of osteomyelitis, which is a severe, deep-seated bone infection, skyrockets.
Because at that point, the infection isn't just in the flesh anymore.
Right. It's literally eating into the skeletal structure.
As terrifying as an infected ulcer is, the guidelines also highlight a completely different condition that mimics an infection but operates on a totally different mechanism. Active Charcot neuroosteoarthropathy.
Also known as Charcot foot.
Charcot foot.
Charcot foot is a structural collapse. It presents with a foot that is suddenly red, hot, and severely swollen. It looks identical to a severe bacterial infection.
But there is no bacteria involved.
None. It is an entirely sterile inflammatory process.
So what is actually happening to make it red and hot if there's no infection?
Well, the neuropathy alters the blood flow and the nerve signals to the bones themselves. The bones weaken, becoming almost like soft chalk.
Oh, no.
And remember, the patient continues to walk on these weakened bones because they don't feel pain. The intense stress causes microfractures all over the bones.
Okay, so the body must try to heal that.
It does, but it overreacts. The body responds to the fractures with massive inflammation, which bizarrely triggers cells that absorb bone, making them even weaker.
Wait, so it's a massive feedback loop of destruction.
A very rapid one. Within weeks, the bones shatter, the joints dislocate, the arch of the foot completely collapses, resulting in what's clinically called a rocker bottom deformity.
So the foot becomes permanently severely misshapen.
Yes. And because it's a sterile inflammation, clinicians can't track it with bacteria cultures or standard infection labs. They have to use infrared thermometry.
Measuring the heat of the skin. So they take the temperature of the healthy foot, take the temperature of the Charcot foot, and compare the delta.
Exactly. If the Charcot foot is significantly hotter, the disease is still actively destroying the bone.
The temperature delta tells them when the inflammation is finally subsiding, which, read in the guidelines, can take several months.
Often 6 to 9 months, easily.
And that brings up the treatment protocol for both a severe plantar ulcer, an ulcer on the bottom of the foot, and an active Charcot foot. Here's where it gets really interesting and honestly super counterintuitive.
Yeah, people are always surprised by this.
The 2023 guidelines state the absolute gold standard for offloading a plantar ulcer is a non-removable knee-high total contact cast. Wait,
Yep.
if the ulcer is just a localized spot on the bottom of the foot or the Charcot inflammation is isolated to just the arch, why on earth are we putting someone in a massive heavy cast that goes all the way up to their knee? That seems like punishing a stub toe with a straitjacket.
It definitely sounds extreme until you look at the physics of walking.
Yeah.
If you just put a thick, soft pad directly on the bottom of the foot over the ulcer, the patient still steps down. The weight of their entire body, say 180 pounds, is still compressing that foot against the ground. The tissue is still being crushed, just against a softer surface. To allow an ulcer to actually heal, or shattered bones to solidify, you have to intercept that 180 pounds before it ever reaches the foot.
Okay, but I'm trying to visualize how a cast does that if the foot is still at the bottom of it.
Think of a standard plastic traffic cone.
Okay.
If you drop a baseball into the top of a traffic cone, the ball falls halfway down and gets wedged against the tapering sides.
No. It never touches the ground.
Exactly. The human calf is shaped exactly like that cone wider at the top, tapering down to the ankle.
Oh, I see. So the rigid walls of the knee-high cast grip the calf muscle. When the patient steps down, the force travels from the ground, up the hard outer shell of the cast, and transfers directly into the calf, bypassing the foot entirely.
Precisely. The foot is just hovering down there inside the cast, like the baseball in the cone.
Wow. That is brilliant.
It bears almost zero weight.
Yeah.
Furthermore, the fact that it is non-removable is a calculated psychological necessity.
Because human nature is predictable.
Very. If a protective device can be taken off, a patient will take it off to shower or, to walk to the kitchen at 2 in the morning.
Right.
For a severely neuropathic foot, those 30 unprotected steps to the fridge can completely undo 3 weeks of cellular healing.
Unbelievable. So a non-removable cast forces compliance. But the guidelines emphasize that spending months in a cast, waiting for bones to fuse or a hole to close, is really the ultimate last resort. The priority is making sure the skin never breaks in the first place.
Prevention is everything.
Which brings us to the 2026 industry advancements. An industry guide from DT Footwear mentions that specialized therapeutic footwear reduces the incidence of diabetic foot ulcers by 51% compared to conventional shoes.
Cutting the risk of amputation in half just by changing what a patient wears on their feet is an incredible epidemiological win.
Seriously. Yet the same guide points out that 22.4% of diabetic patients are currently wearing the wrong shoe size or width.
Which basically guarantees the exact friction that causes the callus, the internal bleeding, and the ulcer we talked about earlier.
Right. So the guide showcases this shoe, the Apis 9735. It's a therapeutic shoe built specifically for severe swelling and Charcot deformities. And get this, it goes up to a 14E width.
A 14E is truly massive.
Right. Standard retail wide shoes might hit, what, a 4E?
If you're lucky, yeah.
So is a shoe that wide just a clown shoe, like a blown-up extra-large sneaker, or is there fundamentally different engineering happening inside?
Oh, it's totally different. If you just magnified a standard sneaker to 14E, the foot would slide around everywhere inside it, creating even more friction.
Which defeats the purpose.
Exactly. A 14E medical shoe has strict internal architecture designed to lock the heel firmly in place while providing immense volume exclusively where it's needed, which is usually over the instep or around badly deformed toes.
So the internal volume manages the pressure.
Volume, yes, but also structural control. The guide details the use of motion control midsoles and very firm heel counters. You see, many patients overpronate, meaning their foot rolls inward heavily with each step.
Okay.
In a neuropathic foot, overpronation puts devastating repetitive torque on the big toe joint. So a medical-grade midsole uses variable density foam. It's super rigid on the inside edge to physically block the foot from rolling inward.
Actively correcting the biomechanics of the gait.
Yeah.
That's fascinating. The DT Footwear Guide also highlighted the Anodyne number 24 Sport Move, which features this patented heel assist technology for hands-free entry. Basically, you just step right into it. At first glance, I thought, well, that sounds like a convenience feature for lazy people.
A lot of people think that.
But the guide points out that an estimated 30% of diabetic patients have limited joint mobility due to obesity, arthritis, or the neuropathy itself.
Right. It is entirely a safety feature. For a patient with severe limited mobility, just bending at the waist to struggle with laces causes a massive spike in blood pressure and becomes a huge fall risk.
Wow, I hadn't even thought of that.
Yeah. If putting on the protective shoe is physically exhausting or dangerous, the patient simply won't wear them around the house. They will walk barefoot.
Which is exactly how ulcers start.
Exactly. Removing the physical friction of putting the shoe on dramatically increases medical compliance.
Amazing. And the shoe is just the outer shell. We have to look at the interface between the foot and the shoe itself, the insole.
The unsung hero.
Right. The current clinical standard relies on heat-moldable plastizo inserts. Gentle heat is applied, and the foam perfectly maps the contours of the patient's foot, distributing their body weight across the entire surface area instead of letting it concentrate on, say, the heel or the ball of the foot. But the research from the University of Texas at Arlington really caught my attention here.
Oh, the UT Arlington patent, yes.
UT Arlington recently patented a dual-layer insole apparatus that represents the next generation of pressure management. They aren't just taking a static mold of the foot, they are actually analyzing the dynamic pressure of the gait.
It's a huge leap forward.
I was reading through the mechanics of that patent. They map out the specific millimeter zones on a patient's foot that experience high stress during the physical act of walking. They then engineer a custom insole with 2 distinct layers. What is the physical advantage of separating the insole into a top and bottom layer?
Well, the layers serve 2 completely different biomechanical functions. The top layer, which is in direct contact with the foot, is designed strictly for shear stress reduction.
Shear stress.
Yeah, side-to-side friction. It allows for tiny micro movements. So when the foot slides slightly forward or backward during a step, the top layer slides with it, absorbing that friction so the skin doesn't tear.
I get it. And the bottom layer?
The bottom layer is engineered for vertical load displacement. Using the pressure mapping data you mentioned, they alter the density of the bottom layer in very specific zones.
Oh, so?
So if the ball of the foot takes too much downward force, the foam underneath that exact spot is made softer, allowing the bone to sink slightly. Meanwhile, the surrounding foam is firmer, transferring the body weight safely to the arch.
It actively manipulates the physics of the foot strike.
Yes, dynamically adjusting to the patient's unique walking pattern.
Which sounds incredibly complex to actually fit. I mean, historically, getting a 14E shoe with custom dynamic dual-layer orthotics meant a patient with limited mobility had to travel to a specialized clinic, get messy plaster casts taken of their feet, wait weeks, and go back for multiple fittings.
A logistical nightmare for someone who struggles to walk.
Exactly. But the 2026 guide highlights a massive shift in how this care is delivered today. It can now be done entirely remotely by just taking photos.
The logistics of fitment have been completely revolutionized by digital spatial analysis.
Really, just from a phone?
Yep. A patient or their caretaker can just use a standard smartphone to photograph the foot from multiple specific angles.
But how does a 2D photograph tell a remote fitment specialist the complex 3-dimensional volume needed for, say, a severely swollen foot or a collapsed Charcot arch?
It's all in the software. The imagery is analyzed using software that measures the pixel dimensions of the foot against a known reference object in the photo.
Like what?
Often, something as simple as a standard credit card placed on the floor right next to the heel. Since all credit cards are the exact same standardized size, the software uses it as a scale.
Oh, that is so clever.
Right. By triangulating the angles from 3 or 4 photos, the software calculates the precise circumference of the instep, the exact width of the metatarsals, and the depth of any bone deformities.
And then they just build it.
The specialist uses that 3D volumetric model to select the exact shoe chassis and engineer those custom insoles without the patient ever having to leave their living room.
It is a brilliant removal of friction on multiple levels. They are removing the literal physical friction on the foot through engineering and the logistical friction of getting the medical care through technology. Let's synthesize the journey we've been on today. We started by looking under the hood at how peripheral neuropathy basically unplugs the body's natural pain alarms, turning a minor rub into a massive hidden injury.
The silent danger.
Then we explored the rigorous clinical systems, from the synergistic danger of the sandbag classification to the wild traffic cone physics of a non-removable knee-high cast that doctors use to literally save limbs.
And finally, we uncovered how modern footwear architecture uses variable density foam, 14E volume management, and remote spatial mapping to act as a daily preventative shield.
So what does this all mean for you, the listener?
Well, when you zoom out, the implications of this go far beyond just diabetes. We're really talking about the profound impact of our physical environment on our cellular health.
How so?
Think about it. If simply engineering the internal architecture of a shoe can intercept abnormal biomechanical forces and reduce a catastrophic event like an amputation by 51%, it completely reframes how we should view everyday objects.
It really makes you look around the room differently. I mean, we spend our entire lives in contact with manufactured surfaces. What other objects are secretly acting as preventative medicine?
Or causing hidden damage.
Right. The office chair you sit in for 8 hours a day, the mattress supporting your spine for a third of your life, the angle of the computer mouse you might be holding right now. We think of these things as just furniture, accessories, but they are constantly manipulating our biomechanics.
Very true. Our long-term health is heavily dictated by the objects that support our weight. If that support is misaligned, the body eventually pays the price, whether it's through a foot ulcer, chronic back pain, or joint degeneration.
If you are driving a car and you know the dashboard warning lights are broken, you don't just keep driving aggressively and hope for the best. You upgrade the tires, you reinforce the bumper, and you change the way your vehicle interacts with the road. The therapeutic diabetic shoe isn't just an accessory. It's the tires, the bumper, and the road, all rolled into one highly engineered package.
That is a perfect summary of the stakes involved.
Well, that is a wrap for today's deep dive. Stay curious, and we'll catch you on the next one.